All right. My name is Kenton Born. The primary thing I'm going to be talking about today is a tool I created called PSUDP, but I'm going to be covering a few other things along with that I've been researching over the last year and a half. I've been working with Honeywell FM&T out of Kansas City for the last 2.5 years, and working on a PhD part-time on the side through Kansas State University. And in my school research, a lot of the stuff I've been looking at has dealt with covert communication, primarily in DNS. Before we get started here, though, I was up in Vegas about 4 months ago, and when I tried to log into Facebook, I was down on the casino floor about to give a presentation, and it came up with a CAPTCHA because I was in a different location. And I thought it was really interesting, and was curious if it wasn't a case of actual location-based CAPTCHA, because it actually came back and wanted me to type in "not winners." I thought that was very appropriate, being on the casino floor at the time. So I just thought that was really interesting and thought I'd share it, and thought it was pretty good advice. And at that point, I went up and played with my new Android phone in my hotel room for the rest of the night instead of gambling. So a basic roadmap of what I'm going to be covering. First, I'm going to go over a little bit of a DNS refresher for anyone who isn't real familiar with it. Talk about covert channels a little bit, and DNS tunnels. I'm going to go over some of my past research a little bit. One part of that deals with browser-based covert data exfiltration over DNS. And then I'm going to talk about n-gram frequency analysis and visualization to detect DNS tunnels. And then I'm going to go over some of my current research, which goes over passive covert communication over DNS. The rest of it's primarily going to be active. And the difference between active and passive with my talk is when in active, I'm referring to actively generating packets, creating new network traffic, whereas passive, I'm referring to using traffic that's already going through the network. So you don't actually ever create a packet of your own. There are two types of covert channels that are generally talked about. You have storage channels and timing channels. Storage channels are basically where there's a location that is written to and read from. The easiest way to think about it is has a detectable effect on. And then there are timing channels, which is transmitting information through time values corresponding to the same data. You can either have a time interval where, say, you either send a packet or don't send a packet on that interval, and that represents a binary 1 or 0, or you can have different time values representing different symbols, which gives you a little more bandwidth. There are a lot of different uses for covert channels. Most of you are going to be familiar with this, so I'm just going to go through it very quickly. One of the primary uses is bypassing network policies. A lot of people will use DNS tunnels, for instance, to get by paywalls, where they'll block the HTTP traffic until you pay them a fee, something like that. They're used for data exfiltration, command and control channels for botnets, that type of thing. And detection basically runs your entire gamut of tools, your network intrusion detection systems, firewalls, policy, traffic visualization. Most of you will be familiar with most of this, so we're going to kind of skip over this part. Now, DNS is essentially a transactional protocol that resolves domain names to IP addresses. It does do a lot more than that, but with what we're talking about today, this will pretty much get you by. You basically have queries where, for instance, your system is going to ask where is a domain name, in this case demonstration.example.com, and you're going to get a DNS response that gives you an IP address. And there may be more than one answer. They may give a list of 3 or 4 IP addresses, and we'll talk about that. But it'll basically give you an IP address. It is at 10.00.45. Down at the bottom, I have a bunch of different names that I'm going to be using throughout the speech. So just familiarize yourself with those. Everything in between the dots in a domain name is called a label. And the combination of all the labels is known as the fully qualified domain name. To the furthest left, you have the LLD, or lowest level domain. Furthest to the right is the top level domain. The furthest to the right, you have the domain. Everything to the left of that, subdomain. So just be familiar with those terms, because I'm going to be using them quite a bit. The actual packet format is as shown here. First, you have a header that has an ID in it, and then a bunch of flags. You don't have to know the specifics of that for this talk. And then this is sort of important. You have a bunch of what you see over at the far right, the QD count, AN count. There are 4 different types of resource records in a DNS packet. You have the question, which there's generally 1 resource record there. Then you have answers, which you may have 3 or 4, which I mentioned earlier. And then you have the authority resource records, which will give your authoritative name server. Then you have additional resource records, which will usually be things like glue records and that type. And then all the different resource record types generally have the same format that you can see below, with the question having a little bit less data. Now, there are a lot of different methods of hiding data in DNS, and a lot of previous presentations at Blackhat have talked about some of these. For queries, by far the most popular is hiding data in the subdomains, and I'll go over that more specifically in a little bit because it is so commonly used, and that is easily the highest bandwidth. But people will do things like hide information in the ID number of the packet. They'll go ahead and strip the ID number that was put in it and put their own custom ID that transmits information. You can drop back to like UDP and change the port and use a custom port to pass information. You can use timing, and you can use the various flags. Sorry, I thought I heard someone say something. And then for responses, there are also many different methods of sending data in DNS. A lot of people will use custom CNAME records, once again putting custom subdomains on there to fit data in there. You'll see a lot of the DNS tunnels right now will use text and null records because you can pretty much put arbitrary data in there and nothing cares. You don't need some specific format per se. You can encode it into IP addresses. You can once again use timing, and once again there are many others. Basically, what to get out of this slide is there are just a million ways of hiding data inside DNS traffic, and there really is no way of stopping them all. Instead, you want to mitigate the ones with the highest bandwidth. Now, exfiltration over subdomains, there are only certain characters allowed in domains. You have A through Z, lowercase and uppercase, 0 through 9, dashes and periods, which basically lends itself ideally to using base 32 or base 64 format. But you have to modify it slightly because there's one or two characters that don't work in domains. So you just change that character to something that is legitimate, and you use base 32 or base 64. And what you'll want to do is whatever data you want to exfiltrate to a certain domain, you'll set up some listener at that server, a domain that you control or that you can at least listen to, and you're going to take your data and you're going to base 64 it in this using this method, and then you're going to cut it up into the labels, place it in the subdomain, and send the queries to the server, and DNS just inherently is going to eventually deliver that packet to that server where you can strip the data out, and then in the response you can put whatever you need to send back to the client. Now, minimizing the traffic when you do this type of thing is important because you don't want to be shooting off 500 queries in a couple of seconds because of behavioral analysis. So typically you're going to want to do some sort of data compression before you do this. But one thing you have to watch out for at that point is character frequency analysis, because compressing the data is going to increase the entropy of it. And once you do that, entropy is basically your randomness. And typically data is shown to all languages, including domains, which I'm going to show in a little bit, basically have certain characters that show up more than others. Everyone's played Hangman. It's on the same premise. So you want to make sure you don't, you're not sending too much random-looking data through it. And then encrypting the data is also important, but once again, you're probably going to be increasing the entropy there. There's a lot of popular DNS tunnels out there. Is there anyone out there that has actually created one of these tools? Okay, no one's in the house today, so I can say whatever I want about them and I won't be wrong. A lot of people have heard about Ozyman DNS. That's actually one that was created by Dan Kaminsky a couple of years ago, another one of the presenters here. TCP over DNS is another popular one, Iodine, DNS to TCP. Basically, all of these just allow you to create, to send data back and forth. Most of these are used to tunnel things like HTTP over DNS, things like that. But you can really, they'll do it at the TCP layer, the IP layer. Ty Miller a couple of years ago showed reverse DNS tunneling shellcode. Heyuka was an interesting presentation. I'm not sure if I'm pronouncing that correctly, but it was a pretty interesting presentation where he put binary data in the domain name labels, which I'm not sure I'd recommend, but it was interesting that he's able to do it. And that lets you fit 8 bits per character instead of 5, which is, it's always helpful to be able to put a little more in there. And then he showed using the EDNSO extension to DNS, which for those of you who haven't heard of that, what it'll do is allow you to extend the UDP packets, which for DNS, they're typically allowed 512 bytes. With the EDNSO extension, you're able to make that up to something like 4,096, I think. And then it also spoofed packets across an IP range, which is really good for behavioral analysis because you don't have a flood of queries or responses coming from one system. So there's been a lot of interesting previous work, but all of this work is dealing with active traffic. They all create packets while they're trying to send data back and forth. While I was studying all these different DNS tunnels, they all had one thing in common. They all require foreign executables both on the server and on the client, which isn't always a good thing. It's something that can be detected. You may not have the required privileges to do this. And I was trying to think of a way of doing that, being able to do that type of data exfiltration, but do it more covertly and be able to do it on any system. So I started thinking about JavaScript, which doesn't require elevated privileges on the system, and it exists just about on every system, and it doesn't have much of a fingerprint. All you'd really have to do is type something up in Notepad and load it up in the browser, which is already an executing process. And if you're able to get this bidirectional DNS traffic back and forth, that would be a pretty covert thing. Typically, a lot of people will look at HTTP traffic pretty heavily, but they'll usually overlook DNS a little bit. So the problem is that JavaScript doesn't give fine-grained access to DNS. There's no API into it or anything. So what you have to do is find a way of separating the HTTP traffic from the DNS traffic in JavaScript. So I set out to try and find a couple ways of doing that. For this example, I'm just going to be looking at exfiltrating a document over DNS through JavaScript. And the only way to really load a document up into the browser is going to be through your typical DOM form input type file. So that's how you can get the file into the system. And the first thing you have to do is break it down into a binary string and encode that into your legit DNS characters, which is the modified base64 form I showed you a while back. So you have your binary string, you compress it, encrypt it, and base64 it. Then you can break that into labels that you can stuff into multiple queries to exfiltrate out. Now there's something called DNS prefetching that's been coming around the last couple of years, and what it does is it resolves domains ahead of time so that HTTP request will be quicker. Typically, whenever a request is made, say for an image on a website, it first has to make a DNS request before it can make the HTTP request. Well, now what they're doing is they're resolving all those domains ahead of time so that when an image or you click on this is primarily for anchor elements. When you click on an anchor element, it's not going to have to send out that DNS request first. It can just send out the HTTP request. And this is pretty much now implemented on all browsers. And you can one thing you can do is hard-code it into the head section and say, we're going to need all of these domains, so go ahead and prefetch them immediately. And while this would work, it's going to require multiple steps. You're first going to have to generate all these statements, and then you're going to have to load it up in a new file in the browser. And it doesn't offer reliability or two-way communication. It's just going to be a one-shot, spit all the DNS queries out. So instead, how I went about doing this was I'd actually dynamically create these anchor elements with JavaScript. And what happens is when you dynamically create an anchor element, set the href on it, and then the second you add that to the body of the document, it'll shoot off the DNS request to prefetch that. So it actually separates it out from the HTTP request. So then you can use that to control all your queries. But this still doesn't let you do any sort of bidirectional communication. But it does give you a way of doing this dynamically and in your code. One thing you'll also want to do is mitigate the amount of DNS traffic you're sending. So you also want to implement some sort of sleep function or use set timeout. And I have a fun little way of using set timeout, which is completely unnecessary for what I've shown you so far, but it'll come in necessary later. And the slide's actually a little botched, but it's interesting. Right at the very top, you have this function called generate queries. You test to see if it's the last query. If it isn't, you call set timeout, generate queries again, which is going to recall this function a second later, just as a way to time it out a little bit. Then it's going to go down, create the anchor element, then set the href to it to the next necessary LLD, the next piece of data you want to exfiltrate. Then you set it to the domain you control, and then give it any random resource. It really doesn't matter. Then when you append it to the body, that's going to send out your DNS request. But then just kind of remember this technique because we're going to come back to it later where it becomes more necessary. Now, what if they have prefetching disabled? you're still actually able to separate the DNS from the HTTP here without exploiting prefetching. You have to think what happens when you set the source of a dynamically created object. Let's look at images now instead of anchor elements. The second you set the source, it's going to send out the DNS request, and then it's going to follow it up with an HTTP request. But the HTTP request won't be made until the DNS response is received. Well, the first thing you can do is just return NX domain from the name server, or from the domain server. And when you do that, it doesn't have a domain it doesn't have an IP address to send the request to, so it just can't do it. An NX domain reply basically means that doesn't exist. We have no idea. So the browser will be unable to make the HTTP request. One problem is that a lot of people, once again, going into the behavioral analysis, may detect that there's hundreds of NX domain replies going through the system, and that may throw some flags. So what you can actually do instead of that is black hole the requests until they time out on the server side. And when you do this, the NIDs will not see the NX domain replies. However, the problem with this is that the JavaScript will halt for long periods of time when this happens. It'll actually sit there and wait for that DNS request to come back before it'll continue on. So you got to find a way to mitigate that. Now, once again, this takes us back to that little technique I was showing earlier with the set timeout. Now we've changed from creating an anchor element down at the bottom to an image element. And once again, when we set image.source here, it's going to send out the DNS query, but then it's going to halt. Well, in this case, it's not going to matter because it's going to call this generate queries again. I actually put generate next query there, but it's going to call generate queries again, and it's still going to continue down and generate the next LLD at the bottom. And you're going to go ahead and send out your next packet. And what you're going to do is you're going to build a little queue of halted threads until they time out in the end. Now, for bidirectional communication, the first technique you can use is timing channels. You're able to use a conditional test to determine whether or not a packet should be sent for a current interval, or once again, you can replace in that set timeout call where I had set timeout every second, you can replace that second with a function that generates how long a timeout should be to represent some symbol that you're wanting to send out. And you can use that for communication. And once again, for the reply back from the server, you can just calculate how long that reply took and then use that to determine what symbol was sent back from the server. And then this isn't going to give you a lot of bandwidth, but it's easily going to give you enough for things like reliability and sequencing and things like that. And then you're actually able to create a storage channel as well by alternating back and forth between NX domain responses and timing out. What you can actually do is right after setting the image.source in this case, where it's going to time out whenever you black hole, you can have a data structure afterwards that actually keeps a binary response from the server. Anytime NX domain is received, it's going to fall through and actually set that sequence number to true in the data structure after it. Whereas anytime it's black holed, it's going to halt at image.source, and it's not going to come through, and it's still going to be the array is still going to be false at that point. So you actually build a binary storage channel response in that way. And one thing I thought about, and I was surprised I'd never actually heard of this before, but I thought it was kind of funny. One thing you can do just to play around with cybersecurity. I've never seen this out in the wild or anything, but I thought it was interesting. It's actually very easy, and just with a couple lines of code, you're able to create JavaScript that'll randomly generate these really long subdomains, and then you can actually use whatever domain you want. You don't have to control it. But if you just create these very long subdomains of random nonsense data, you don't actually have a file or anything. You can throw this on any website or execute it in your own browser, and it's going to make that computer look like it has some sort of data exfiltration or DNS tunnel scenario coming out of it, when in actuality it's just some harmless JavaScript running in the background. But it's going to look very malicious, and they may scramble and try to figure out what's going on there. But I thought it was interesting how easy it would be to actually mimic a DNS tunnel or basically an owned box without actually doing anything to it. Now, DNS tunnel detection, I'm going to talk about this a little bit, character frequency analysis, and then I'll get into PSUDP. Lengthy subdomains is easily the easiest way to detect it. All of the DNS tunnels I talked about earlier and all the most popular ones out there, they all have very long subdomains because they're trying to squeeze as much data as possible into every one of the packets. And that's really just an obvious telling sign in that case, and then also large amounts of traffic. Both of these are really the low-hanging fruit, and they're the easiest way to detect all sorts of DNS tunnels out there. And another actual very good method is doing statistical analysis on the resource record types. Like I mentioned earlier on responses, a lot of the tunnels will use null or text and resource record types. And those really aren't seen that often to most systems in a network. There are a couple that are going to be sending out a significant amount of traffic with those. A lot of blacklists and things like that use them. But for the most part, most systems should not be using those types of resource records much. So if you see a lot of them, it's really a red flag that there's something going on there. But this is really an underused method. I'm surprised there aren't more tools out there that do this. Neural networks were actually used by Jared Hind. He talked about this at DEF CON 17 last year. And he actually had really well-chosen training material using things like lengthy subdomains. But I'm not real excited about the idea of using neural networks. I think just some custom thresholds and algorithms would probably do the job just as well. But his idea for the training material kind of set me on my path on what I started studying. And then finally, you can do n-gram frequency analysis of subdomains. And I created a tool and presented previously called ngviz. I'm going to show you a couple slides on that. Basically, the idea behind character frequency analysis is the same as Hangman. There are certain characters that are going to show up more often than others. This was primarily brought about by Zipif and Shannon. Shannon was popular for calculating the entropy of the English language. Now, domains aren't necessarily a language themselves, and I wasn't even sure if they'd particularly match up to English incredibly well, since there are a lot of different random domains out there. I mean, you have like the cartoon site XKCD. You have a lot of random things. I wasn't sure how well that would work. So what I did was I actually mined the million most popular domain names of 2009 and ran n-gram frequency analysis on that. For n-gram, I mean unigrams, bigrams, and trigrams, groupings of 1, 2, and 3 characters. And the results I got were actually absolutely amazing. This is a graph for unigrams for one character showing the frequency of how often the character showed up compared to its rank. By rank, I mean the top most showing up character, the second most. And then over on the right, you can see a little graph that shows you with domain or English on the left and domains on the right, how well the character ranks matched up. And you can see it's actually amazingly accurate. So I started thinking this may be possible. So what I created was this tool called ngviz. And what this does is it allows you to load up a fingerprint of your typical network traffic. What you do is you'll record your network traffic for however long you'd like, and you load this up into the system as the fingerprint of what the traffic should look like going through the network. And then what you do is at any other point, you take any captured traffic and throw it into the system. You can either separate the traffic out to analyze each IP address separately or each domain separately, in case you have several IP addresses all using the same domain for something. And it'll separate each of them out and analyze them separately, and then give a percentage match to the fingerprint of what legitimate traffic should look like for character frequencies. And what this actually came out with some pretty amazing results. Here you can see there was about 20 simulated users here, and what they were doing was actually just going to popular websites out there and crawling them, taking every domain and subdomain in, they'd go, it'd visit those, and so on and whatnot. And then I also ran 3 tunnels through the system at the same time, iodine DNS to TCP and TCP over DNS. So this is what it looks like when I clicked on one of the simulated users. And you can see everything that shows up in green is something that matched very well. So both the rank and frequency are matching pretty well on most of those. White and yellow are a little less of a match, and anything red is bad. Now when I go down and click on one of the tunnels, you can see immediately both the rank and frequency are absolutely terrible in all of these. And in this case, all the simulated users came in between an 81% and a 60% match, whereas all 3 tunnels were between 43 and 35%. Match, which was really pretty significant. You can see over on the right, switching back and forth, the red line showing how the characters matched up with each other. You can just tell a huge difference there. And it's even more pronounced once you look at the chart of frequency versus rank. You can see all 3 of the tunnels immediately shot down to the bottom and stuck out like a sore thumb. So this actually gave me a lot of hope for this actually being a pretty interesting method of detecting DNS tunnels assuming the low-hanging fruit methods didn't work. If they ever were to go back and actually fix those and make it to where they actually did use very short subdomains and were a lot more covert about it, then this may be a backup method that would be able to detect that type of thing. All right, now I'm going to start talking about the passive side of things, what I've been working on recently with PSUDP. And essentially what I'm calling it is exploiting the slack space. This is what the domain label format looks like in a DNS packet. When you have a domain, like in this case www.example.com, the dots aren't actually placed somewhere in the packet. What you have is each of the labels separated by the length, before each label is the length of that label, specified in 8 bits. So before www you have a 3, then you have a 7 for example, a 3 for com, and then each domain is ended with a 0-length 8-bit segment. And as I mentioned, you can have several answers resource records in a packet, which means you're going to have to list the same domain over and over again. Well, DNS came up with what's called a compressed form, which is actually, it's optional. It can be used or it cannot be used. Resolvers have to be able to handle both ways. But what it can do is, instead of listing the same domain or even part of a domain, for instance, if later on in the packet we want to refer to example.com, not www.example.com, you can actually just create a pointer instead of putting one of those length segments in there and point back to any point in the packet previously. So in this case, we're pointing back to the 7 and saying we just want from that point on. So we want the example.com portion. So this allows the packets to fit a little more information. It compresses them a little bit. And this will be important for a technique we look at here in a little bit. Okay, the DNS protocol does not specify a length anywhere in it, and for the most part, it's if you're given what the answer is, it's ambiguous what the length would have been, because there are so many valid ways of forming it. You can use compressed form, you can not use compressed form, you can only use compressed form in a couple places but not others. You can do whatever you want with it. So for length information, you generally have to look at the IP or UDP layer. So the first question I started asking is, why not just modify the IP or UDP lengths and use that slack space as a storage channel? In that case, you'd be able to store binary data instead of characters, which gives you, which lets you fit more characters in there. And generally, for the most part, security tools do not analyze the slack space. So this is a basic idea of what I'm talking about here. You have your IP header, UDP header, DNS header, then you have your DNS data. Well, what you can do is you can just take the IP and UDP lengths and increase those by the amount of injected data you want to throw in that particular packet. And then you're going to have to recheck some, put a new UDP checksum on there and a new IP checksum on there when you modify it. But essentially you can put however long of a covert channel on the end of this you want, and you can put any type of data in there. It doesn't have to be formatted in any specific way. And this will actually exist going through the network until it hits a DNS resolver at some point. Now there's actually a way of creating this slack space in the middle of a DNS packet instead of just shoving it on the end, which is even better, especially when it comes to detection. I'll talk about that in a minute. But what you can do is you can take one of the labels from the beginning of the packet. You can actually move that to some place very far in the UDP packet after you've extended that, and then you can actually take one of the pointers that's supposed to pointing to it, and instead have a pointer that points forward in the packet, which I'm actually absolutely amazed DNS servers and resolvers allow. But you're actually able to have the pointer point forward instead of backwards. And what it'll essentially do while it's parsing this DNS packet is it'll completely skip over that injected data portion when it is looking at this packet. Because there isn't anywhere in the packet that says you need to look at this position, then this position, then this position. It just follows the flow of the packet, follows the pointers, and whatnot. So you're actually able to put this injected data somewhere in the middle. I'm really surprised that's accepted. Now, as far as detection goes, the first general attempt you're going to do is worry about the injection at the end of the packet. So what you can do is you can parse the entire DNS packet, see what length you covered, and then compare that to the actual UDP length and see if you actually are at the end of the packet or if there's still space there. And if there is still space, then there's a good sign that something was injected in it. But this is going to miss the more sophisticated covert channel using the pointer manipulation, because in that case, they actually are going to travel to the end of the UDP packet, since you're actually, your slack space is now in the middle of the DNS packet. Instead, you can try to keep track of every location in the packet that is legitimate while you're going through it, and then check for holes, kind of like a taint analysis type thing. But that's more complicated than is actually necessary. What you have to do is you have to ensure the end of the packet is reached and that all pointers point backwards. If both of those hold, then you're able to detect anything going on there. Now this is an example of a DNS response that I injected some information into. This is actual, if any of you have heard of Rickrolling with Rick Astley's Never Gonna Give You Up. What I did is I actually put the entire lyrics of Rick Astley's Never Gonna Give You Up onto the end of this DNS response. And as you can see, looking at it with Wireshark here, it's saying we have a standard query response, no errors, one question, 5 answers, so on and whatnot, and it doesn't care less. And unless you actually look at the raw data of this, you're never actually going to see what's there. And now, while it sticks out like a sore thumb here, there's obviously going to be a lot of methods of making that much more covert. A, you're going to make it smaller, and B, use non-character values. Like if you look at the start of the packet there, you have a bunch of dots, things that can't be interpreted. It'd be very simple to use the method where you stick data in the middle of the packet, and they just come out to look like dots like that. Who honestly can look at a DNS packet, a raw DNS packet, and say what's going on there? So it's actually pretty effective. So the tool is called PSUDP, and it's a kind of a triple play on words on why I chose that name. First of all, it kind of stands for PSUDP, or PostScript, that which comes after the writing. What I'm doing is I'm sticking data, sort of an actual second UDP protocol on top of UDP. After the actual legitimate packet, which is where the pseudo UDP comes in. It's sort of a fake and alternative UDP on top of UDP. And then lastly, because of pseudo UDP, it's UDP, but a little extra power added to it. And of course, another obligatory, make me a sandwich. Some of you will have gotten that. Okay, so there are actually 5 executables in the PSUDP package. 3 of them are for what I'm calling this brokered architecture, and then 2 of them are for a point-to-point system. For the brokered architecture, this is sort of your network-wide covert communication thing I was talking about, where you're going to want some sort of broker at the DNS server that's going to have access to all of the systems and is legitimately going to see network, because once again, we're not actively creating packets, we're just looking at legitimate packets going through. So it needs to be on a system that sees as much traffic as possible from as many different systems. And what it's going to do is store and forward messages between clients. And then you have your clients, which inject DNS messages to the broker and listen for incoming messages from the broker. And both of these programs are going to be running all the time. They're constantly on. So what you have is a third executable, PSUDP, which is responsible for passing messages up to the client to send out, doing that through a Unix domain socket. So it's just a quick send this message, okay, and then it exits. And then the client will hold on to that, waiting for passive traffic to throw it onto. And then for the point-to-point system, which I demonstrate with the injector and listener here, is sort of a data exfiltration file transfer, is what I'm going to be demonstrating here. And for all these, they're all going to be manipulating the packets using something called LiveNet Filter Q, which I'll talk about more in a little bit. But to kind of show diversity and how you don't actually have to manipulate the packet, I'll use LivePCAP for that. But I'll talk about that more in a little bit. So the basic flow of the brokered architecture on PSUDP, it's basically a messaging system. I didn't create anything that was actually out of the box, could be used malicious in any way. I'm not necessarily in that business. I'm primarily showing what can be done, and if someone wants to go and create something after that, so be it. But basically what the messages do is they piggyback on the legitimate traffic going through the system without ever creating legitimate packets. So if you look down at the bottom design, you have a client. So say the client just opened up their browser and sent out a couple DNS requests. What it's going to do is it's going to look and see if it has any messages it needs to send out to anybody, not necessarily the broker here. If it has a message to send out to anybody, it's going to append that onto the outgoing DNS packet that's going out to the broker. The broker is going to strip that off and send back just a typical DNS response back. Then it's actually going to hold on to that message there. It's not going to deliver it at that time. It's going to wait till the recipient of that message sends a DNS request later, which may or may not have a message on it. And then it's going to append the message that needs to go to that recipient onto the DNS response that's going back. So there's a lot of waiting going on. It's not going to happen immediately unless there's a lot of DNS traffic going through the system. As I mentioned, PSUDP uses LiveNet filter queue, which is a kernel packet filter that allows you to inspect and mangle packets through user space programs. It's usually used in combination with IP tables, where you say what traffic you're looking for. It's going to pass it up to the user space and let you manipulate it and play around with it at that point. It's actually a really cool setup, and it's something I'd recommend people try to play with a little more. I haven't seen a lot of really good uses with it yet, and I think it has the potential for it. And although it's not necessary, PSUDP will actually fix the packets before it finishes delivering them to the application layer. But this isn't necessary. It's good hygiene, I guess you could say, but it isn't necessary, and that's seen with the listener executable I showed that uses live pcap instead of netfilter queue, where it just listens and doesn't modify the packet at all before it reaches its destination. Because it's important that all these packets still work as intended. None of these are going to cause a problem with any of the programs. Now, as far as message management goes, the clients basically just keep a linked list of messages that they still need to send out that have been passed up to them from the PSUDP executable. And anytime it sends a packet out, it's going to look, see if there are any messages to send out. If there are, it'll throw one onto the DNS packet and send it to the broker. The broker will detect these messages, and it keeps a hash table using the destination as a key, and each of the elements are a linked list of messages intended for that destination. So anytime it receives a message, it'll throw it into the appropriate linked list, and then anytime it's going to send a response out, it'll check this hash table for that destination. If there are any messages in that linked list, it'll throw it on there and send it out. Demo time. Now this demo I have been struggling with severely because at home I had an 8 gig system where I could have 3 virtual machines, each with 2 gigs apiece, and things were beautiful. Now I have 2 gigs in all. So I'm going to try and do this with just two virtual machines. So it won't be quite as fancy as a demo, but it'll still work. All right. Probably should have colored these differently, but here on the left we have the broker, on the right we have the client. The first thing I'm going to do is show exfiltrating a file, just point-to-point system. All right. Give me a second for some setup here. All right, so we're going to call the injector. And then also you can specify as a flag a certain domain you want to be injecting to. So say you have, like with DNS prefetching, you may have DNS queries going out to all sorts of different domains. You may want to focus on a specific one. So we're gonna say google.com. And then we're going to give it the file we want to send. In this case, we're going to send the Rick Astley lyrics. Okay, it's read the file in, it's ready to go, but it's waiting because there aren't any DNS responses going or queries going through the system right now. Now we're going to come over here, set up our listener, and he's listening for google.com. So now what we're going to do is we're going to go over to the other browser, or go to the other system here and just browse. Once again, it's looking for the google.com domain, so we're just going to visit that here. The second we hit that website and the DNS request started going through the system, over here we have the lyrics spit out. We're no strangers to love, you know the rules, and so do I, yada, yada, yada. Most of you probably are familiar with that song. All right, now what I'm going to do is actually do the brokered architecture. In this case, as I said, by the time I get the third virtual machine up, things crawl to a halt. So I'm actually going to cheat a little bit here and send it to my own system. I'm going to say send this message to myself. So it's going to jump to the broker, and then the broker is actually going to send it straight back to the client. All right, so we got the client going here. Now we're going to set up the broker. Should be good. All right. So both the broker and the client are ready. As I said, they're both running all the time. They're waiting for data. So now we're going to come over and run that third executable, the PSUDP program that passes messages up to the client through a Unix domain socket. Actually, I have no idea what the IP address is. All right, so we want to send this to 24.120.50. Okay, there we go. Okay, so it says we're sending hello Blackhat USA 2010 to this IP address. But right now it's still waiting at the on the client because there's no DNS traffic going through the system. So now we're going to open up our browser again. And here we go over at the broker. We received the message. Okay, so we got a message from 24.120.250.120 going to the same IP address. Hello, Blackhat USA 2010. So now back over here at our client, we see that it went ahead and received that message. Now, in this demonstration, everything I've been doing has been dealing with DNS. But the kind of the important thing to think about on this is that it's not limited to DNS. This is essentially something that can be done with any protocol out there. In this case, I use DNS because it's one of the most common protocols out there, and it's pretty much going to give you access to any system in the network because everything does use DNS and uses it all the time. But you could do this over essentially anything with that Slack space method. And I'm really curious why I actually haven't seen more dealing with that. This does have the downside over other DNS tunnels that it's not going to persist through several layers of DNS servers. It's either going to be point-to-point or it's going to make it through routers and everything that's dealing at the UDP or TCP layer or anything like that. But once you have things interpreting it at the actual application layer, then that tunnel that storage channel may disappear. So that is a downside to it. But it is still a very effective method, especially when you're able to, in most cases, set your own DNS servers and tell it where you actually want it to point to. So it's really pretty powerful in that aspect. And that's really about all I have. So I'm open to any questions you have, and thanks for listening to the talk. Yeah. Say that again? Then it'll just simply backlog it and store it in that linked list until it actually does see the traffic. Yeah. You can either give it a PCAP file and it'll strip out all the domains for you, or you can just give it a file of domains that are going through the network. Yeah. Yeah. For which application here? For which architecture are you talking about? Yeah. You should be able to do it any way you want. In this case, I programmed the system to do it to a specific domain because you're typically going to only have control of one domain out there or be able to listen to one. But I mean, you could just as easily take that check out of the code and have it just exfiltrate the data to any domains being visited. So I mean, there's no specific requirement for that. I'm not sure if that's what you're asking or not. Yeah, they don't care about domains because your broker's typically always going to be what the client is sending its traffic to, like an inside internal DNS server, something like that. Like it's primarily say there's 5 or 6 owned box in a network, and you're wanting them to communicate, so they're not all trying to zip a file out and exfiltrate it. Maybe they all want to collaborate in some way. You're basically assuming that they're going to see each other's traffic in some way. Yeah.
One channel I didn't see show was the use of sequence numbers.
Let me think. I don't think does DNS have the sequence number? It has the ID number. I think that may be the same thing. Yeah, I think, what's her name? I can't think of it, but I know which one you're talking about. It is very possible. It's a much lower bandwidth is the problem. You can get very little data. You're able to use that. There's a lot of flags in DNS you're able to use, and all of these they're going to get you a few bits here and there, a few bits per packet. Whereas like subdomains, you can get 200 bytes out in a subdomain, or in a lot of the responses, you can get 400, 500 bytes out of it. Or if you use the eDNSO extension, you can get a lot more than that. So really, you just have to give up on those kind of tunnels and just not even worry about trying to find them, essentially. Because there's bigger fish to fry, I guess is the thing to say on that. Is that it? Thank you.